In this video, we're going to go through some basic combinatorial structures and their associated ordinary generating functions. So to start, we're going to be talking about combinatorial classes. So a combinatorial class is a set A that is finite or countably infinite, and it has to have a size function. And we'll usually denote the size of an element of A with just absolute value bars, or if we want to be specific about what class we're using, we'll use the class as a subscript. And so size, we'll see in examples exactly how this plays into things, but for now the size function just needs to be a way of associating a non-negative integer to each thing in the class, and the set of alpha of a given size has to be finite. So we'll usually write this, if our class is A sub n will be the set of things in the class with size n, and this has to be finite to be a combinatorial class. And the cardinality of this set will just be A sub n, and these are the terms of the counting sequence that we're interested in. Here's just another notation for cardinality. So our counting sequence will be A0, A1, A2, and so on. So let's see this in some simple examples. So our first example is the set of binary words. So this, by word, I guess I need to be a little flexible. I just mean all sort of lists formed with zeros and ones. I also include the empty word, which I'll just write with an epsilon. So that's just no word. It has size 0. But so each one of these will give me different binary words. And the size function in this case will be just the length of a word. So the size of 0, 1, 1, 1, 0, 1, 0 is just the number of zeros and ones here, which adds up to 7 in this case. And so then this curly wn will be the words of length n. And it's not too hard to convince yourself that the number of words of length n in this binary alphabet is 2 to the n, just because you have two choices for each entry. So you'll just do 2 times 2 times 2 times 2 all the way to the number of all the way to the length of the word. Okay, so not too bad. Let's look at permutations, which we've already mentioned. So the combinatorial class of permutations is easiest to define by breaking it up into sizes. So a permutation of size n, so curly p sub n, will be bijections from the integers 1 through n, and that's some special notation that our book uses right here. So this bracket 1 dot dot n will be the integers 1 through n. So permutations of size n will be bijections from the set of 1 through n to 1 through n. And if you've learned about permutations before, you're probably used to different notations for these. The most simplistic notation is just to write out where every element goes. So this notation here means we're writing out the permutation where 1 gets mapped to 3, 2 gets mapped to 4, 3 gets mapped to 1, 4 goes to 6, 5 to 2, 6 to 5. And this is just sort of a functional notation. You're just saying where everything goes. And we've already mentioned in the first lecture that the number of permutations of size n is n factorial, just because we have, in this example where n is 6, I have 6 choices for the first spot, but then I can't repeat anything, so then I have 5 choices for the next spot, 4, 3, 2, 1. So this is the combinatorial class of permutations, size being the set that the permutation is built on permuting. And here's maybe a more exotic example. Triangulations T of a convex polygon with n sides. And so size here will be a little funny. It'll just be the number of triangles in our triangulation. So this is best seen with a bunch of examples. So the triangulations of size 1, that's just a single triangle, because here the polygon has 3 sides, and so things of size 1 would be a triangulation of a triangle, and there's just one of those. So you get T1, our counting sequence is 1. And then next, I have triangulations of a convex polygon with 4 sides, which gives me the subclass T2. And this is just ways to triangulate a square. So we think of these polygons as sort of fixed on the plane, and then we're looking at all different ways to draw lines through them. So the associated counting sequence would have T2 equals 2. And then next I look at triangulations of a fixed pentagon. And I think if you go through it, you'll get 5 of them. And then I went through and saw that the number of triangulations of a fixed hexagon is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so this is maybe good to go through an example like this to see how you would build the triangulations from a lower example, but we'll come back to this example later. So here are these values I've listed out. It turns out one can show that Tn actually has a simple formula in terms of binomial coefficients, and these are related to Catalan numbers. Okay, and let's get into generating functions and so forth. We do need to have this definition first. So two combinatorial classes A and B are going to be considered isomorphic, and we'll write this if they have the same counting sequences. So an equals bn for all n. And the reason for introducing this is because we're only interested in sort of the counting sequences of the combinatorial classes for a lot of what we're doing. Obviously, these things have other structures too, but the main thing we'll be studying initially is just these counting sequences. So in the invitation to analytic combinatorics, we talked about binary trees, and it turned out that they had the same counting sequence as triangulations, so these two are isomorphic, even though it's not completely obvious why they might be. Okay. So now it's easy to associate an ordinary generating function to a combinatorial class. So given a combinatorial class A, its ordinary generating function, OGF will be our abbreviation, will be A of z, and so its coefficients will just be the terms of the counting sequence, A0 plus A1z, A2z squared, and so on, which we can write as an infinite sum here. And we'll be thinking of this just as a formal power series. Initially, we don't worry about convergence right now. You can treat it just as an algebraic object. Another way to think of this formula for this ordinary generating function is in another way. Turns out if we just do the sum over everything in the class of z to the size of alpha, you get the same thing, because the way this sum would work is you would regroup things according to size, and so if you regrouped it, you'd exactly get the power series you have here, because anytime I have z to the n, I could collect those terms, and there would be a sub n terms with size n, and so I would exactly get the OGF. But this is sort of a conceptually simpler way of writing the OGF. Okay, and so back to these examples. The binary words, their counting sequence was simple. It was just 2 to the n. And so its OGF is the sum of 2 to the n, z to the n. And this is just a geometric series. So using this formula for geometric series, which holds for formal power series too, you get that binary words have this generating function. The permutations have this generating function. And so here we're just throwing n factorial in as coefficients. It turns out, this will only converge at 0, so its analytic properties might be difficult to deduce since it's hard to make any sense of it in terms of actual numbers. But turns out, if you look at the book, there's a place where it gives a hint that you could. Anyway, the triangulations have this formula. Again, I haven't derived this, and we'll see where it comes from later. But we already, in the invitation to analytic combinatorics, saw that these were the coefficients of the binary plane trees. And we had an exact formula, but it's not so important right now. But these are just to illustrate some of these ordinary generating functions. Okay, next we'll talk about some ways to generate new combinatorial classes from old and see how you can build all kinds of interesting examples out of them.